All right, hello everyone, and welcome to our webinar on limiting corrosion using electrically conductive materials. We're going to get started in just about 10 more seconds. I see folks are still joining the room here. All right, so welcome everyone. My name is Jared Cohen. I'm the Marketing Communications Manager for Parker Chomerics, and thanks for joining us today. All right, just a few housekeeping details for you. Please make sure you are in listen-only mode if you're not already. You should have all joined in listen-only mode. And please ask questions. This is one of the best benefits of webinars is we're able to answer your questions live. So on the bottom of your screen in the panel, you'll see a quick Q&A button. Go ahead and submit your questions anytime during the presentation, and we will answer them at the end of the webinar. And also, don't worry, this webinar will be recorded and be sent to you automatically after the call. So whether you've attended or have not attended, but you've at least registered, you will receive an email with the recording. So no worries there. All right, so today's speakers, introducing Sierra and Ben. Hey, Sierra, are you there?
Hey, how's it going, everybody? Thanks for joining. My name is Sierra Eiden. I'm the Defense Aerospace Market Manager for Parker Chomerics, and I'm a mechanical engineer, and I've been here about 10 years.
And hello, everyone. My name is Ben. I'm also with Chomerics for about 3 years, and I'm the Market Development Engineer for the Mid-Atlantic.
All right, thanks, guys. So today's agenda, we're going to start with a little bit of an introduction to Parker Chomerics and who we are. And then we'll get right into it, talking about what corrosion is, and then we'll start to discuss our corrosion-resistant particle technology. And then we'll get into how we take that technology and implement it into our products. And then we'll get a little into how test methods and procedures are created to then measure and test against the products that we create. And then finally, the all-important is the Q&A. So make sure you are asking questions and throughout this presentation. So a little bit about Chomerics. We are a division of Parker Hannifin, and we are the global leader in the development and application of EMI shielding and thermal interface materials. Our core competencies are in material science and process technology. We offer a market-driven product development cycle, and we like to feature our integrated electronics housings as one of our go-to-market plays, and we are also proud to offer custom engineered solutions and integrated global supply chain management for all of our customers. So with that, let's get into corrosion.
All right, so diving right in, we're going to start with a little bit of what corrosion is and some of the factors that impact it. So the main topic of corrosion that we're going to be talking about today is known as galvanic corrosion. And one of the important things to note is that there are 3 major causes of galvanic corrosion, all listed here. So the first one is that you have to have a difference in electric potential between 2 different metals. Sometimes this is known as dissimilar metals, or when you have 2 different types of metals in a system or in an enclosure. The second factor that's a main cause of galvanic corrosion is an electrical path between the 2 metals, also known as a conductive path. And a lot of the times when it comes to EMI shielding, that's met by an EMI gasket or a sealant or a conductive paint. And finally, the last major cause of galvanic corrosion is that there has to be the presence of an electrolyte, which typically is a fluid such as atmospheric humidity or salt fog that ends up having the ability to break down either of the 2 metals or both.
Thanks, Ben. So, we talked about the difference in galvanic potential between metals. And what you want to do in order to mitigate that is you want to try to minimize the difference in the galvanic potential, which means you want to try to make sure that the materials you choose are close on the galvanic series. For instance, like if you have an aluminum housing, you would choose a silver plated aluminum gasket. You're trying to keep those close on the galvanic series. A presence of electrolyte, fluids, salt fog, humidity, you're going to want to reduce, if possible, eliminate the presence of an electrolyte. So, you can use a beryllium spring finger gasket, but that's not going to prevent water ingress or moisture intrusion. So you want to use a conductive elastomer gasket. And if possible, you would want to try to put an additional environmental seal, possibly. But, the tricky part is the conductive path between interfaces. So, Ben, why shouldn't I just powder coat my entire box and be done with it?
Well, as much as providing or removing that conductive path between the two interfaces would absolutely help minimize galvanic corrosion. Unfortunately, it's the nature of an EMI gasket to cause a conductive path between those two interfaces. So in order to meet EMI shielding requirements, it would really be almost impossible to eliminate the conductive path.
Good point.
So now talking about some of the costs of corrosion, according to the Government Accountability Office, corrosion ends up costing the Department of Defense more than about $21 billion a year. And a lot of that is in the form of rework or increased maintenance schedules, mostly caused by harsher environments. So here we've got 4 different types of environments, each of which is kind of seen across the board in terms of applications that Chomerics deals with. So when it comes to Class A environments, that's typically a controlled indoor environment, a lot of the time seen with life science or indoor telecom applications. Typically, they're not really exposed to weather. So you don't see a lot of galvanic corrosion in environments such as Class A. When it gets to Class B, that's where you have an uncontrolled outdoor environment, an exposed application such as automotive, a lot of outdoor telecom applications, industrial, and when it comes to defense and aerospace, it's ground vehicles, shelters, things like that. When it gets to Class C and D, that's where you really need to take into account a lot of the material choices when it comes to minimizing galvanic corrosion, especially with the presence of salt fog in marine applications or the constant exposure to weather and rapid temperature changes in aerospace applications. It really is going to be the harsher environments that will speed up the galvanic corrosion and create a lot of cost in the system.
So, why do we focus on corrosion? Because we want our box to work in the field for a long time. But Ben, what do we mean when we say improved field reliability? I mean, I have a 20-year field life requirement. I designed my box. I got my EMI gasket. Okay, so what's the problem?
So one of the principles that we talk about a lot is known as shielding decay. What ends up happening is that shielding performance actually can drop over time as a result of corrosion. And a lot of the times that's due to the oxides that build up on the surface of the interfaces. So what happens is as corrosion builds up, you see shielding performance drop over time. And sometimes over the course of that life cycle, over the course of that 20 years, you may not be meeting a lot of the requirements that you originally designed in the first place.
And, we talked about having to maintain an electrical conductive path, but, what about a dual seal? I mean, I could just add a secondary gasket to the outside. Wouldn't that make everything fine?
Yeah, absolutely. A dual seal would typically be a great solution. The problem is sometimes it can be costly or you just don't have enough real estate in your designs to be able to incorporate a 2-seal system.
Okay.
Some examples of 2-seal systems are things like co-molded or co-extruded gaskets. What that can include is basically a conductive and a non-conductive material extruded or molded in parallel, where the non-conductive material prevents the conductive material from weather. A lot of the times we'll see this in a seal-to-seal design as well. So next, we're going to get into some of our corrosion-resistant particle technology. The particles are really what drive a lot of the corrosion resistance in a lot of these systems. So if you're looking at this table, what you see on the left, the metals, is known as the galvanic series. You'll see them ordered actually in terms of how noble or how active they are, with the ones at the top being more noble or less reactive.
So Ben, why does it matter if materials are more noble or more active?
Typically, when it comes to galvanic corrosion, when you have 2 different metals, the material that's less noble, or in this case, lower down on the chart, ends up being the one that's corroded or eaten away or dissolved fastest. So if you look here, you can see aluminum, which is a very common material in a lot of applications because of its cost, its weight, its workability, ends up being lower on the galvanic chart, which means it can actually take the most damage in a lot of systems. That's why you see the fillers on the opposite side, on the right side of the chart, used to make sure that you're getting the best possible interface and minimizing the difference in that potential.
And one thing I want to point out too is on the left, you see all the different materials, different metals in the chart. Most likely, you're not going to be able to get a pure copper gasket. if you look on the right at our typical fillers, you're going to have something that's a silver plated copper or a nickel plated graphite. So it's really important to pay attention to the metals with the fillers and try to minimize the galvanic corrosion, galvanic differences, and bring those closer together. So this is a typical chart. This is a chart that's found in our catalog. These are typical housing design materials. So, you know, first one on the chart, 6061 T6 converted coating, class 3 finish, our nickel plated aluminum particles, passivated silver plated aluminum, which has been a gold standard of corrosion for years. Those are all excellent choices. When you move down the chart, as you saw in the previous chart, magnesium is a very active material. It's very difficult to gasket a magnesium housing. I know it's very attractive to a lot of engineers because of its low density, but it's just not recommended in conjunction with EMI gasketing.
And really what we've done with this table is we've taken that galvanic series and done a lot of the testing at 168 and 504 hours salt fog exposure of our gaskets as well as the enclosure materials. So we've really put together a determination of what the best mating materials are in terms of minimizing that corrosion and increasing the life cycle of a lot of these applications. So here we see just a couple examples of some of our conductive fillers. And really, like I said before, they're the driving force behind the corrosion resistance. Each filler is going to have a different shape, a different morphology, a different density, and they're all going to have unique applications in terms of EMI shielding, conductivity, as well as corrosion resistance. And that's where we look at deciding which is the best one on an application by application basis.
So this is a typical shielding curve run on a pretty standard mil spec test, a solid D extrusion tested for EMI shielding. And you notice the top curve is the nickel aluminum by itself, not run through any kind of testing. And then we take it and we run it through a 2000 hour, 125C dry heat. We do 1000 hours at 85, you know, humidity and temperature, and also the 500 hours salt fog. So you can see the curve, actually the shielding decays and lessens over time. So corrosion really affects your ability in the field to resist susceptibility and also not radiate its own EMI interfering with other electronics around. So it's very important to realize that yes, you designed it perfectly, but over time you will see some shielding decay.
And here's just another example of the similar particle technology in nickel-plated aluminum, but incorporated into a robotically dispensed form-in-place gasket. So again, we see the same principles that shielding decay over the course of various environmental tests. And it's important to note that this isn't a material this isn't a property that's unique to this material. It's something that all EMI gaskets are going to go through as they're exposed and used in the field over the course of time. So next, we're going to talk about some of our corrosion resistant products. So the incorporation of a lot of that particle technology into various filler systems.
So these are typical fillers, nickel aluminum and silver aluminum. They're pretty standard. Nickel aluminum's one of the most corrosion resistant materials on the market. And these are various binders we put them into. So silicone, fluorosilicone. There's a lot of ways we put our fillers into, you know, various materials.
Sierra, in addition to the nickel aluminum, would you say there's another particle that's also good for corrosion resistance?
Yeah, so nickel aluminum is, I like to call it the platinum standard. Silver aluminum's been the gold standard for years. So both of those choices are decent.
Would you see a situation where you use a silver aluminum over a nickel aluminum?
Yes, so actually the nickel aluminum has really good absorptive properties, but its resistance is higher than the silver aluminum. So in a situation where you are going to use not only shielding, but actual grounding as well, I would definitely steer you towards the silver aluminum material.
That's good to know. And here we see another application of where we're taking that particle technology and incorporating it into a different binder. So rather than incorporating it into a silicone or a fluorosilicone gasket, we see sealants and gap fillers as pretty common applications for sealing of flanges. Here we see our Cobon 1077 and 1075 as using those particles in a silicone gap filler. One of the newest technologies that we've been working with and have released is actually the incorporation of those particles into a polythioether base in the form of our Cobon 1018 as well as 1019. And here we had just a little bit more information about what that application of testing looks like. So we see 168-hour and 1,000-hour salt fog testing between the Cobon 1019, which is a silver-plated aluminum in a polythioether, and the competitive baseline. Now, on the left side of every image, you'll see that darker strip. And that darker strip is actually a non-conductive top coat, such as a caulk paint. And what that does is it's typically meant to protect the material from environment. However, with the competitive baseline, you'll see that even over time, that paint isn't able to minimize that galvanic corrosion. Some of the other advantages of a polythioether base is that it's actually a non-silicone based solution. So there's no silicone contamination in applications that have optical requirements. And it's also a paintable system, which doesn't require a polysulfide coating before it's painted. Finally, the polythioether actually serves as a really good resistive material to aircraft fluid exposure in aerospace applications.
Another one of our technologies are corrosion resistant coatings. So this is our 2000 series coating. It's a material, there's 3 versions. So they are, they do have chromates, soluble chromates. The 2000 series is chromate free, hexavalent free, which a lot of states like California, for instance, they have a lot of environmental laws which do not allow you to spray 2000 series with the soluble chromates. This is, they use passivated conductive fillers, and it's a hydrophobic polymer system, which actually removes the electrolyte. So it keeps the water out, the moisture out. This is not meant to just paint your box and be done with it. This is used in conjunction with an EMI gasket, painted over something like an aluminum housing, stainless steel, carbon composite. But this can be a really good solution for very extreme environments. So what you would do is you'd have your aluminum housing, let's say it's aluminum, you put your primer down, you paint your Co-Shield 2000 series in conjunction with the gasket, and then you non-conduct top coat with the rest. So this could be used with the nickel aluminum fillers, with the silver aluminum fillers, but as I mentioned, it's not meant to be a standalone coating. And this is a picture. So we talked about soluble chromates. It's very good corrosion resistant technology, however, with environmental laws. So our 2000 series, this is an aluminum plate. We painted it with 2000. We scratched the plate, put it through the 504-hour salt fog test. And as you can see on the right-hand side, the Co-Shield actually prevented the corrosion from spreading where the scratch was. And even with the 2000 without the soluble chromates, it still maintained excellent corrosion resistance. So it's just slightly less good of performance, but still a good choice.
Now that we've talked about some of our products, we wanted to mention some of the test methods and procedures that we use to go through the testing and analyze how effective these materials are. So the first one and the most common one that we use for our conductive elastomers is actually our TM101 test. So what it consists of is 2 Delrin blocks that act as a support. And between those 2 supports, you have an aluminum alloy coupon that we test under trivalent and hexavalent chromate treated aluminum. And on top of that, we use a conductive gasket. That's our test specimen. So this entire system will go into a salt fog chamber over the course of a certain amount of time, whether that's 168 hours, 504 hours, 1,000 hours. And as an entire system, what we'll do is actually take it apart, rinse off the aluminum coupon, and measure any kind of pitting or loss of material that the aluminum coupon suffered. So as you can see in this image here, on the left, we see a lot of the corrosion resistant materials, the nickel aluminum, the passivated silver aluminum, and you'll see how much better the coupons look, as well as how much less material in terms of that aluminum that was dissolved away, as opposed to something like a nickel graphite or a silver glass.
So what you're showing me is that I'm probably not going to use a silver glass gasket in a very corrosion environment, huh?
Exactly. So in this case, probably don't want to use the silver glass on a shipboard or an aerospace application. But it's important to note that there's a lot of great applications for silver glass in applications in a Class A environment that don't see as much environmental exposure.
And it's a low-cost material.
Absolutely. One of the things we also wanted to point out is that we have a lot of test methods and test procedures and test reports that we've done on our materials, including our co-seal elastomers, our co-shield paints, even our conductive form in place gaskets. And all of these studies can actually be found on our website. So please, by all means, feel free to take a look at those and understand how we went through the testing.
So Ben, I see a 1298 elastomer in conjunction with the 2001 coating. What if I wanted a 6503 nickel aluminum and a 2003? You know, are we able to do testing in-house at Chomerics?
Absolutely. We have a full test services center with test chambers for EMI testing, as well as an R&D center where we do a lot of the environmental exposure. So by all means, if you've got a specific environment that you want us to analyze, if you want us to take a look at certain temperature ranges or temperature fluctuations, that's absolutely something we can test. So feel free to reach out to either Sierra or myself. And finally, just as a last wrap up, we want to go through some of the steps and tips and tricks that we talked about in this presentation that really should help you avoid seeing a lot of the damage caused by galvanic corrosion. So the first one that we've mentioned several times is the use of a nickel-plated aluminum filler wherever possible. It's really going to help from a shielding effectiveness. It's going to help from a corrosion resistant. And a lot of the times it can be a more cost-effective solution because it uses a nickel as opposed to a commodity metal like silver.
Yeah, and silver-plated aluminum, obviously it's been the gold standard of corrosion for years. It's a mil-spec material. It also has excellent ability to ground as well as shield, so it's definitely a good second option.
The next step would be to utilize a seal-to-seal design. So this is kind of one of the two seal methods that we've used. And instead of having a gasket made up against two interfaces, you actually have a gasket on each interface. So the seal-to-seal method provides you the same level of environmental sealing and is used a lot in aerospace applications. But the benefit is that you're actually minimizing the difference between galvanic materials because the seal should ideally have identical galvanic series.
Yeah, and we talked about when you have the ability to put a second seal, you know, a non-conductive outboard, a conductive inboard, but we also have co-extruded with one side being non-conductive, the other being conductive, as well as we can mold custom shapes with conductive and non-conductive. So that's always an option, really eliminate the electrolyte altogether.
Additionally, depending on your requirements, you're going to want to look at surface treatments. So different types of platings of aluminum or steel or tin or nickel, as well as additional top coats like a caulk paint that can protect from the environment.
Avoid designs that allow moisture to pool, dripping in water ingress. You know, you want to keep the moisture out as much as you can.
One of the main things that we recommend with our conductive elastomer gaskets is actually staying as far away as possible from a dovetail groove. We do not want to see dovetail grooves. And one of the big reasons for that is that the sharper edges of a dovetail groove can actually damage the conductive gasket and cause some of that conductive filler to create FOD. Now that FOD is typically a pure metal or a metal with silicone or fluorosilicone. So it can cause some corrosion depending on where that FOD lands.
You can always get another protective coating and use additional environmental sealants, you know, caulking things up with silicone or putting top coats on.
And lastly, we talked about this earlier, try avoiding magnesium wherever possible. It's a very reactive material. And when it comes in contact with other less reactive material, we see a lot of damage to that magnesium housing.
Yeah, and if you guys were on our last webinar last month, I talked about why to avoid magnesium. We had a customer that had designed a magnesium box because they had serious weight concerns. They came in for an EMI gasket. We actually painted the housing with our Coast Shield 2000 series. And when we put it into the salt fog chamber, we didn't realize that the painter had actually, there were pinholes in the paint. And so when the housing came out of the salt fog chamber, it was literally a shell of 2000 series paint. The magnesium completely disintegrated. So just avoid the M word. No magnesium. And with that, thank you guys for joining. Hopefully that was a good, quick little lesson on corrosion. And I guess we'll start answering some questions.
Yeah, I see a couple questions have come into the chat box there. You guys
So,
able to see those?
I see why are 6502 and 6503 max operating 125. I don't know the answer to that question, but I can tell you 65 and 6503, there is no MIL DTL 83528 spec for the nickel aluminum particle itself. So until the government decides to add a nickel aluminum particle to a MIL spec, there is no MIL spec for nickel aluminum. However, we have tested it to the MIL spec and it passed. So, I mean, it's an excellent performing material.
It's also important to note that there's a lot of customers in the defense and aerospace sector that will do their own testing and qualification of the 6502, 6503 material. And many of them actually already have. So it'd be surprising if defense customers are looking at these materials and haven't already gone through the process of at least analyzing them upfront. We also had a question about, would it be possible to get a copy of this presentation? So this entire presentation was recorded and will be available up on our website to watch on your time and as many times as you would like.
Yeah, I have a question from Jordan. Are there any relevant MIL or industry standards that your products are qualified to? Absolutely, yes. And there is we have our conductive elastomer catalog on our website. Each material will list the different specs it's qualified to. And then of course, if it's not in the catalog, you can always ask and we can let you know. If there's a specific industry standard you're looking for, then feel free to reach out. But yes.
Sierra, we'll include that catalog with the copy of this presentation to everyone who's here automatically. So you'll be able to see that.
Excellent.
We have a question from Scott. He says, in my application, I have a chem-coated aluminum house with a co-sealed 1298 pad touching down directly onto an ENIG finish on a PCB. Great data on the chem coat side. Do you have any data on compatibility with different printed board finishes in salt fog environment? We do have a little bit of that information. It's something that's come up relatively recently, and we've had our research and development team actually look into some of the coatings. So Scott, please reach out to either Sierra or myself, and we'd be happy to connect you with that information.
The acidified salt fog test is a requirement that's flowed down more frequently. We actually do not do that test in-house, but we have done that test at outside labs, and I believe we have information on that.
One of the questions we have is, how does PSA play a role in corrosion? That's actually a good question, and it's important to note that we actually have two different types of PSA when it comes to our elastomers versus our molded gaskets, or our extrusions. So our extrusions actually utilize a non-conductive PSA, and that PSA doesn't have any conductive fillers and therefore doesn't add any additional metal to the system. So there really isn't any impact from the PSA in a lot of extrusion profiles, such as hollow D or solid D, that end up still using the conductive elastomer as the main material to get that electrical contact, as opposed to the PSA. When it comes to the conductive PSA, we've also used passivated materials in that PSA, and so we've seen very little impact, if any, of corrosion caused by PSA, especially considering the relatively low amount of material in the PSA relative to the gaskets and relative to the size of the housings or the flanges.
Another thing to note about PSA as well is that typically you use that as a third hand. It's not meant to be something these gaskets are going to be in compression. So typically the PSA would be non-conductive. It's stronger, and then you rely on the gasket itself to do all your grounding.
One of the important things that I wanted to touch on is we've mentioned our conductive elastomer engineering handbook quite a few times. And if you can see my screen, up in the first few sections, in addition to EMI shielding theory, is we have a whole section on corrosion resistance. It includes a lot of great information on the galvanic series, the different types of environments, different finishes that we would recommend, as well as the test results and a lot of the information that we covered today. So please, by all means, feel free to look through that, ask us, find information about what you're looking for. You know, here's a seal to seal design, and different gasket aspects that we look for.
Yeah, there's a question about thermal spray coatings. We would have to look through our test database where we have some of our previous materials. A lot of times we do this specifically for customers, so it may be something that they have provided to us. We may not be able to provide to you, but I am not personally familiar with thermal spray coatings myself. Are you, Ben?
I'm not. I haven't seen much in terms of applications where that's been a concern, but by all means, we've got an applications team that would be happy to look into that.
Mm-hmm.
One of the questions is about low temperature materials. So a lot of our gaskets end up actually going down to sub 45, sub 50 C, down to minus 60 in some applications. So the materials work at a relatively large temperature range. So by all means, please look at the conductive elastomers in terms of their qualities and their specifications.
Okay, let's see. So what would be the best elastomer to use for galvanized steel sheets? The nickel aluminum has the best corrosion resistance and compatibility of all of the materials. So I would say the nickel aluminum.
We have a question here about silicone versus other PSA materials, when to use them, pros and cons. I'm assuming this is referring to the use of silicone in terms of spot bonding. So a lot of the times when it comes to mating our gaskets into a groove or into an application, for a more permanent bond, we can either use a PSA that's meant to be a third hand in the assembly process, or using a silicone or a fluorosilicone RTV to spot bond the gasket in. A lot of the times we look for a non-conductive RTV, partially because we've seen that conductive adhesives don't really have the same strength. They also do tend to add a little bit of a foreign material or an additional metal, which can lead to galvanic corrosion. But in general, spot bonding, as long as it's used relatively conservatively, so you're not putting down a ton of material along the entire length of the gasket, it can be a good way to maintain EMI performance and sealing performance while maintaining the gasket in a groove.
Okay, and then just to follow up with the test data for coatings versus our gaskets, we would have to look and see exactly which specific tests that we have. So I would say shoot us an email with the specific thermal spray coating, and we can look a little deeper on that one.
Great. So are there any more questions?
I know a few of you raised your hands when we were talking about our Cobond 1019, our conductive silver-plated aluminum filled in a polythioether. By all means, we have a lot of test data as well as qualification data and shielding effectiveness performance on the data sheet and additional literature. So please feel free to reach out. We have a lot of support that can help with determining whether it's a good fit for your application.
Good point, Ben. Thank you.
All right, if there are no more questions, then we will wrap up here. Well, Ben and Sierra, thank you guys very, very much.
Thank you.
Have a great day, guys.
Take care. Take care, everyone.